Hello and welcome to the High and Continuous Demand LOPA Considerations web seminar. I'm Eric Scharf and I'll be presenting today's material. We've got a fair bit that I'd like to cover in our talk today, and it mainly centers around how to apply the layer of protection analysis technique as effectively as possible to not only low demand mode applications, which the process industry has established quite effectively, but also to high demand applications or continuous mode applications where the potential safety function that we're looking at is actually expressed as the failure rate of the initiating event in an event sequence. So that fundamental difference is really what we're going to be looking at today. And our objectives are pretty much aligned with all of that. So we're going to consider, again, regardless of the application, a high demand mode or continuous mode is modeled with the LOPA technique in very much the same way. And one of the interesting things, and we'll talk about this a reasonable amount as well during the presentation, is that the LOPA risk analysis approach, how it fits into the context of the Machine Functional Safety Standard 62061 and the related Machine Safety Standard ISO 13849, along with their targeted risk reduction or risk management standard, the ISO 12100. As I said before, I'm Eric Scharf. I've been around quite some time now at this point. I've been with exida since we started up a little over 20 years ago now. And the focus of my work is on the front end of the safety life cycle. That is often understanding the risk that we have in the machine or the process under consideration. I'll very briefly introduce exida, but I would like to note that we have quite a number of additional follow-up exida introduction information at the end of the slide presentation. So we will see a fair bit more about that at the end. But basically, exida is a safety lifecycle cybersecurity company. That's it. That's all we do. We really function exclusively in that automation and security domain with functional safety, alarm management, and cybersecurity as our reason for being, essentially, in all of that. So with that in hand, let's continue on. Now, layer of protection analysis and actually even the entire safety life cycle itself are good engineering practices which sit underneath whatever laws and regulations exist in the environment where we're practicing functional safety. And those national laws, acts, and codes, they have priority. They are what is required. And the safety life cycle and the layer of protection analysis techniques are things that we can use to demonstrate and ensure that we are indeed meeting those requirements. And the one that is going to come up most directly in our discussions is the third one from the bottom. All reasonable and practical means to ensure worker safety, or ALARP, and its companion, so far as is reasonably practicable, SFARP. Both of those are often written into the legal code. And layer of protection analysis, as we will see, is going to be part of our method of understanding the risk that we have and how we're managing that risk in order to meet those legal requirements. So as I said, sitting underneath those legal requirements, we have the array of functional safety standards, the 61508 umbrella or basic standard, the 61511 process standard, the 62061 machine standard, and then the companion ISO 13849 and 12100 in all of this. So in applying these standards and applying the layer of protection analysis technique, we're really working with hazard and risk analysis front-end activities, as we often call them. And in these front-end activities, we begin by identifying our potential hazards. And then from that list of identified hazards, we then carry out some level of risk analysis to determine how much we might be worried about those hazards and whether or not we need some additional means of risk reduction in order to manage those hazards down to, or excuse me, manage the risks of each of those hazards down to a level that we can live with. But keeping our eye on the big picture here, this analysis, yes, it's required, but we really don't see the benefits of this analysis until it helps us, until we take it on board and understand the risks that we're dealing with. And then through that understanding, we enact some intelligent set of improvements in our situation to actually take advantage of the analysis that we did in the first place. So with that big picture in mind, we're going to look at our goal, and that is to achieve a level of risk that is tolerable for us. And that tolerable risk concept is something that we're going to need to translate into a set of engineering designs for our safety-related system. Now, how we express that tolerable risk, the standards are completely open about it. The laws, as I said earlier, often require a demonstration that our risk has been reduced to as low as reasonably practicable. But in terms of that tolerable risk, how we define it tends to guide how we look at risk, and similarly how we apply various risk analysis methods such as LOPA to identify any SIL targets or performance level targets that we might need for any safety functions that we apply to our machine or our process to manage that risk down to this tolerable level. So the standards themselves are pretty flexible with regards to the actual details of the analysis. They, in all cases, give some example methods that are presented as informative approaches that are not specifically required to be applied in any particular case. However, the requirement is that the risk be identified, the hazards well understood, or excuse me, the hazards identified, the risk well understood, and then managed down to a level that we determine is tolerable for the process or the machine to be operated and maintained. So all of the different standards give us a lot of flexibility in exactly how we carry out this risk analysis. And there will be a number of things that they will say must be considered in that analysis. And that leads us into the actual details of, all right, what are we doing in our various risk analysis techniques, LOPA included in all of this. Now, in ISO 13849, for instance, it's actually quite interesting that the example method that they present in, as we've copied here, figure A1, actually has an embedded risk tolerance present in it based on their assignment of the definitions for the severity S1 and S2, the frequency F1 and F2, and the probability P1, P2 terms, along with the performance level column, A through E. And by reverse engineering this chart, it's very easy to find out that using this chart as it exists in the standard gives you a revealed risk tolerance of one fatal accident in 1,140 years, or again, applying that PLE, which we see at the bottom, to a fatal S2 accident with no credit for frequency or probability of avoidance in any way. So that alone gives us an indication of some of the challenges in just blindly accepting the standards, that they carry with them some embedded assumptions which may or may not be acceptable in our particular case. And interestingly enough, we have the same situation with the IEC 62061. Granted, it has a slightly different example method of sill target selection, and it lays out similarly a severity estimate along with a frequency of exposure to the event, the probability of occurrence of the event at that frequency, and then a second probability of being able to avoid or limit that harm, given the fact that the unwanted event is going to occur. Now, when we take the example parameters from 62061 and apply those to, again, reverse engineer what risk tolerance we have, in this case, again, looking at the fatal accident criteria, since that's such a defining point for risk, we can see that in applying these example risk graph, in effect, parameters from 62061, we again find that the implied tolerable risk is at 1 death per 1,140 years. Again, that 1 times 10 to the minus 7 dangerous failures per hour. So anytime you choose to use either the 13849 or the 62061 example methods as is, the embedded assumption of a risk tolerance of 1 death in every 1,140 years comes along for the ride. Now, that may or may not be acceptable, and that's where we start to get into trouble. If we blindly apply that guideline, and this is a reference back to the original publications on the concept of ALARV, and we find that that 1 fatal accident in 1,140 years is actually sitting very, very close to the intolerable region of 1 fatal accident per 1,000 years of exposure. And it is well away from the nominally broadly acceptable tolerance of 1 fatal accident per 1,000,000 years of exposure. So again, something you really need to be careful about if you're taking the embedded risk tolerance from the standard examples in 13849 and 62061. So in any case, regardless of which tolerable risk we choose for our particular situation, we're looking at understanding the likelihood and consequence of each hazard, the risk. And again, since we'll be talking today about the likelihood side, let's look at that in a lot more detail. So, frequency of accidents. That's what we're trying to understand with any risk analysis method. So, a lot of times, the likelihood is considered as a chain of events that is set into motion by some well understood and reasonably predictable initiating event. And then the tracking of that event through a series of potential escalation steps to a release of material, and then whether or not that release of material is going to cause personnel harm, equipment damage, environmental harm, etc. So that by understanding that initiating event, in combination with understanding the escalation path from that initiating event to a potential accident, we can come up with a reasonable estimate of how often we might expect that accident to occur. And that's what layer of protection analysis essentially is. Now, there are various flavors of layer of protection analysis. You can look at it in a semi-quantitative way, where each protection layer is an order of magnitude or nothing. Or we can look at it in a more quantitative form, where each protection layer does indeed have an estimated probability of failure in preventing the accident. And regardless of which of those semi-quantitative or more fully quantitative approaches we can use, that is a very useful tool in understanding whether or not we need an additional layer of protection of a sill-rated safety function, or if we need a high demand or continuous mode safety function to sit right on top of the hazard and fail at an extremely low frequency, so that then that low failure frequency of our safety function translates into a suitably low accident rate that we observe on the back end in all of this. So as we mentioned earlier, when we looked at the 13849 and the 62061 examples, those risk graphs actually do have embedded within them the fault propagation of an initiating event, our frequency and exposure to the hazard, along with one or more example protection layers that we must consider in each of those cases. The downside with each of these cases is that we only get 2 potential protection layers to consider in 62061, and in 13849, we actually only have 1 potential protection layer that we are directed to consider in all of this. So if that's good enough, then by all means, apply that method. But if it's not good enough, if you need a better understanding of the risk that you're facing, a better understanding of how that risk is controlled and potentially managed, then protection layer analysis in its more full forms is probably going to be a better approach than using either of the 13849 or the 62061 example methods. So for that more complete analysis, we really need to focus on what makes an independent protection layer workable. What do we need in order to credit each potential protection layer that we're considering? And here we have the 4 standard criteria. Specific, it's got to work. Independent, it must function independently of all other protection layers, because the math that we use to calculate our accident frequency is probability multiplication. And in order for that math to be correct, each protection layer must be fully independent and not correlated with the behavior of each other protection layer. And again, that's the one that is the real core of the LOPA technique, confirming that we've got independence of our different protection layers. Now, dependable, that's pretty much a given. If you want to have a nice low accident frequency, each of your protection layers will be better served by having nice low individual failure probabilities in all of this. And then finally, at the back end of all of this, we have the audit requirement. And that is, and it's laid out in the standards in quite a lot of detail, that is during our operation and maintenance and use of the equipment or the process, we need to be able to confirm that our estimates for our different initiating event frequencies and protection layer effectiveness can be compared to that operating behavior. So that closing of the loop between our estimates in the risk analysis phase and our actual observations during the operations and maintenance phase is another requirement for each of our protection layers. Now, in a machine application, we might expect to have a fundamental control element or not, depending on exactly what we're looking at. Now, there may be a mechanical limiter or a manual emergency stop capability that sits directly on top of that item under control. Or it may be directly controlled by the safety system with an automated independent emergency stop. And if that automated independent emergency stop is required to either act continually to or sense the behavior of that system on a continual basis and be always ready to stop and actually activated on a frequent basis, then that safety function will be acting effectively in high demand mode, and its failure rate is the best way to express our initiating event frequency and understanding the overall potential accident frequency that we're trying to analyze. Then after we get beyond our safety function, we may have either mitigation elements or other late phase protection layers, which can still either eliminate or at least reduce the consequence of our potential accident in question. I would like to note one or two classic protection layers that we see again and again, so we'll highlight a couple of those. And the first of those is our basic process or equipment under control system, or just control system for short. And this may or may not be present in a particular application. But if it is, it tends to be our first line of defense. And oftentimes it is limited by the fact that it has not been designed in accordance with 61508. And it does not have suitable proven in use justification to claim SIL level credit in its operation. So as a protection layer, its probability of failure on demand is limited to 10%. Similarly, if this is our initiating event, we will find that same limit of credit that we can take at the single failure in 100,000 hours, or roughly one failure in 11.5 years or so. So our basic control system is going to be limited by those SIL definitions unless we meet the individual SIL requirements in our design or our prior use of that control system. Now, another factor that we often see that can lead to challenges is the use factor or the time at risk. And there's a very solid logical background for all of this, and that is sometimes failures are benign. The equipment might not be turned on or in use. And if those failures are identified during a pre-start check, they can be corrected outside of operation, and those failures can be eliminated before operation and thus have their risk managed accordingly. Now, unfortunately, those pre-start checks are not always done, and we sometimes find ourselves taking incorrect credit for time at use if we don't have some sort of pre-start check. And also there's a second problem, and again, this can show up depending on how we're looking at our initiating event. If we're looking at an initiating event with an idea of exposure to a particular hazard, that already has embedded within it a time at risk. So if we then later on try and take subsequent credit for a time at risk protection layer, after we've already taken credit for that implicitly in our initiating exposure frequency event, then we really have to keep things sorted and eliminate that double credit. All right, so again, with those two highlights identified, let's look at now how that safety function might fit into our potential protection layer model of accident frequency. As we said earlier, there are two main places where a safety function can fit in a layer of protection analysis. In the process industry, the vast majority of our safety functions sit on top of a separate independent basic process control system. And as a result, that basic process control system manages the process on a day-to-day, hour-by-hour, year-by-year basis, so that our safety function is actually only demanded upon failures of that basic process control system. And those failures typically occur less than once a year. So our proposed safety function acts as a protection layer, and its probability of failure on demand defines its performance and its SIL. However, in some process applications, and actually quite a large number of machine applications, the safety function is much closer to the equipment itself and may indeed be an active control function of the equipment. If that's the case, then the safety function is in a much higher level of use, and with either a demand rate of greater than once a year or a nominally continuous control function or safety control function being required. The way in which that safety function sits in our analysis is completely different. Here, we find that each individual failure of our safety function is much more likely to escalate in harm than it is to be caught and fixed by a proof test. So the PFD average, or PFD, really doesn't work well in this application. So instead, the standards guide us toward a PFH, or a probability of dangerous failure per hour, which is effectively a dangerous failure rate. And that dangerous failure rate is what we would model as an initiating event frequency. And either that translates directly into our accident frequency if we get no additional benefit from any follow-up protection layers, or can be somewhat reduced with follow-up protection layers that would prevent the hazard, or prevent the failure of that safety function from leading to the accident consequences in most cases. So those different roles of our safety function need to be considered properly in layer of protection analysis. So let's look at a risk scenario that has both elements of initiating event and protection layers at play. And I'd like to use an automotive accident example, because in automotive accidents, we often have an inherently high demand function associated with the car brakes, and an inherently low demand function associated with a set of airbags for a car. So let's look at a scenario where we've got a car brake failure that could lead to a fatal crash, and the airbags are one of our proposed protection layers. So in this situation, the initiating event is indeed our brake failure, and we might identify some potential protection layers. And the first one is, I'll just call it driver action. And the driver can potentially use the handbrake if the foot brake has failed, or can use engine braking to take the energy out of the car. The driver can also potentially steer the car to a safe location and avoid a fatal crash. But if our driver intervention fails, unfortunately, now we are looking at a crash, and the airbags come in to hopefully prevent that crash from being a fatal crash in all of this. So taking this situation and putting it into a basic LOPA diagram, we see the initiating event of brake failure. We see the combination of the handbrake, engine brake, and steering to safety considered as a single protection layer. And the reason for that is that each of these different actions still has one element in common, and that's the driver. So since we have the driver action common to all of these methods of avoiding the accident, that means they are not at all independent and need to be grouped as a single combined independent protection layer, as we've labeled one here. Then, as we said earlier, if that fails, the car is going to crash, and we hope that the airbags protect the driver to reduce the frequency of the fatal accident outcome. Now, this is often the easy part of a protection layer analysis. The hard part of a protection layer analysis is determining realistic numbers to put in for those initiating event frequencies and those protection layer failure probabilities. In an ideal case, you're going to have a lot of equipment data, operating data at your disposal from your facility, operated in the way that you operate your equipment, as a foundation reference for estimating initiating event frequencies and failure probabilities. The downside is that, unfortunately, a lot of companies still don't put in all of the required effort to collect that data. And then even if they do collect that data, it's not often analyzed and put into a usable form that can feed well into a layer of protection analysis. Instead, a lot of times we'll be going back to industry average data for failure rates and failure probabilities grouped by equipment type. And a lot of times we still need to fall back on the expert judgment of our risk analysis team to estimate what failure rates and what failure probabilities accurately describe each scenario that they are assessing. So assuming that we get some reasonable numbers, we can put together what I'll call a base design. And this is with basic equipment, nothing up into the sill levels at this point, as our reference risk analysis, our semi-mitigated accident frequency. So we would potentially look at one dangerous brake failure every 10 years. We might look at the driver being effective 5 out of 6 times and a nominal 15% probability of failing to bring the car to a safe state on their own. And a similar base case, airbag effectiveness of 80%, which is a probability of failure on demand of 20% in all of this. So at the moment, we haven't really talked at all about what's the safety function and what's not, and that's fine. This is a straight risk analysis of this scenario with a base case design. So plugging in the numbers, we have our accident frequency equal to our 1 in 10 year brake failure times the 15% of the time that the driver cannot bring the car to a safe stop, times the 20% of the time in which the airbags fail to protect the driver, leading to a fatal accident frequency of 003 per year, or in normal human units, 1 death every 330 years. Now, we expect this to be unacceptable. This is a frighteningly high accident frequency. And we would then look to find some reasonable way to reduce that frequency further than what we've got in the base design. Now, there are 2 different potential safety functions that we might consider here. Now, the first case that we would consider in our LOPA analysis is the brakes themselves. And since the brakes are our initiating event and we're using them all the time as we drive, they absolutely fall into that high demand and continuous mode definition of safety function. So then our brakes effectiveness is what we're going to look to improve in order to manage our risk down to a tolerable level. And let's say, for sake of argument, in the third box down, that our tolerable risk target is 1 death per 10,000 years. Well, we have 1 death in 330 years, so we find that we are out by a factor of 30 in all of this. So we need to improve our situation by a factor of 30. Now, this is just one way to do the math. You can also do the math where the initiating event frequency is a variable, And then you solve the equation with a one event in 10,000 years as the accident frequency target to get the required initiating event frequency that you need in order to meet that target. So fine, either way works, and both of those approaches give us a requirement on that initiating event frequency to be 0033 per year, which, converting it into the language of SIL, PFH, probability of failure per hour, gives us 3.8 times 10 to the minus 7, which sits in the middle of the SIL2 range. So here we have used LOPA to identify a SIL target for our high demand break function of a PFH of less than 3.8 times 10 to the minus 7 and at least a SIL2 overall integrity level in this. Now, that's the high demand mode case, and just for completeness, let's consider the alternate low demand mode case, where we look at the airbags, which are a protection layer. And again, as we already established, the airbags are rarely required to operate to achieve a safe state. And the low demand mode application of these is PFD average. And just like we did previously, we have a requirement of one fatal accident in 10,000 years. We currently have one death in 330. We're still out by a factor of 30, which means that our 0.2 PFD average needs to be cut down by a further factor of 30 to 0067 to hit that 1 in 10,000 year target. So we find that our risk reduction factor of 150 total for the airbags is now required to hit our frequency target for our accident. And again, that also happens to sit in the mid SIL2 range. And again, just like previously, we can rearrange the equations and solve for the variable PFD average of our airbags. Now I just see I've gotten a question, and it's probably best to take this question now rather than wait to the end. And the question is the failure rate of 0.1 per year considered low demand or high demand? Now, a failure rate actually isn't necessarily a low demand or high demand thing. What defines low demand or high demand is how often the safety function needs to operate. And that is the definition of low demand or high demand. So if I have something in basic control with one failure in 10 years, and then I have my safety thing sitting on top of that, the safety thing sitting on top of that is only going to see one demand in 10 years, and that would be low demand. But just a raw failure rate alone isn't enough to make that decision. The real question of low demand or high demand is down to how often do I need that safety function to work to achieve a safe state. And the car brakes are very frequent. We use them all the time. In fact, our use rate of the brakes is probably a couple of times per hour, a couple of times per minute, depending on what kind of traffic we're in these situations. Now, another question, and again, this is also worth considering directly. Testing of the airbag. The proof testing of that is part of a calculation of the PFD average that airbag system will be able to achieve. Now, in actual statistics, there is a specific cutoff point between low demand and high demand mode that unfortunately the standards have glossed over, and that is if most failures are identified by testing, low demand PFD average is a better description of SIL, and the safety function is better described as a low demand protection layer. Whereas if I don't have proof 2 proof tests per demand. Most of the events or failures of my safety function are revealed by escalation, and the failure rate PFH term is a better description of the SIL performance of the device. But the standards have chosen to simplify this down to a 1-year cut point. If a safety function is demanded more than once a year, the standards call it high demand or continuous. And if the safety function is demanded less than once a year, the safety function is termed low demand in all of that. Now, thank you for those questions. All right, so we've got our low demand safety function airbags and our high demand safety function brakes, both demonstrating here that they can each individually achieve the 1 death in 10,000 year target by improving their performance by a factor of 30 from our base case design, which in the low demand case gives us a total risk reduction factor of 150 for the airbags. And in the high demand case gives us a total dangerous failure rate of 0033 per year, or 3.8 times 10 to the minus 7 PFH. So again, LOPA helps us look at the overall situation, including consideration for high demand elements, including consideration for low demand elements in all of this. And LOPA, therefore, hopefully, can give us a better overall picture of the risk that we're dealing with. And that's what we've got on the next slide. Because again, if we are subject to an ALARP requirement, reducing our risk down to a level as low as reasonably practicable, we need to understand that risk well. And layer of protection analysis is a great tool to help us understand that risk. So it allows us to consider an array of different potential protection layers, an array of different potential initiating event frequencies, and how sensitive our overall risk is to improving each one of those different situations until we get down to a point of diminishing returns, which is what the ALARP guideline requires. Now, there's a lot of things that we can look at in considering all of the different options. And I've pulled this from the ANSI B11.6 machine safety standard. And it has the classic machine industry guidelines for risk reduction priority. And absolutely at the top of that priority list is the question, is there a way I can eliminate that hazard by doing something differently, or substitute some other method that has a lower inherent risk associated with it? So that elimination substitution at the design level is the first thing that we would want to consider, and layer of protection analysis can absolutely analyze the effectiveness of that option. Then, second in the hierarchy, we often have guards or passive safeguarding devices, and this can also be considered in our layer of protection analysis. Moving further down the list, active safeguards, safety instrumented functions, and things along those lines sitting in the level 3 option. And then finally, training, PPE, work procedures, etc., which sit at the back of the queue in terms of managing our risk here. So the layer of protection analysis method can flexibly consider how much advantage we can get from each of these different risk reduction options. Now, again, it's worth a slide to cover this, because a lot of times we see some of these things ignored in risk analysis, and that is, again, at first principles, the less stuff you have, the smaller the crash is going to be. The less you mess with something, the more rare a problem is going to arise as a result of messing with that something. So those two considerations at the inherent risk level are a very useful starting point. Now, hand in hand with all of that is layout. And this can either be in a process plant, keeping people away from the dangerous materials, or in a machine operation system, keeping people away from the dangerous machines. Now, obviously, geographic risk in the machine environment can have little enforcement elements of gates and guards, and that is very effectively managed in all of this. Other means of risk reduction. Now, the standards themselves highlight a fair number of other means of risk reduction that we should consider in each particular case. And we can look at examples of equipment casings, physical barriers, or other walls, mounds of stuff that partially contains either process fluid or flying bits of metal, depending on exactly what kind of risk we're dealing with. And again, these other means can also be considered as part of LOPA in all of this. Now, I've gotten another question that is also probably worth clarifying at this point, and that is now, I'm sorry, let me read this directly. A BPCS is demanded continuously, so it is like the brake. So for the initiating event control loop failure, yes, that control loop is operating in high demand, and it may or may not be a safety function. And what that means is that whether or not it's a safety function or not, as the initiating event, it needs to be treated as an initiating event frequency in our overall risk analysis of the situation. Okay. All right. So then, continuing on, 13849 is a combination of performance and prescription, whereas the safety lifecycle standards are pretty much focused on performance. There are other various codes and standards out there which have a very specific prescription set or prescriptive set of requirements as to what you must include in a safety function. And when you're faced with a combination of performance and prescription requirements, you end up having to meet both of those. And this can lead to problems because in a lot of situations, there will be an idea that, well, I've got a SIL rated safety function. Why do I have to meet the prescription requirement? Well, unfortunately, that is a case of because it's the law. And if you have a performance requirement and a prescription requirement, you must meet both of those requirements in parallel to ensure that you have met the overall requirements for operation of your system. Now, this comes up again and again with e-stops. For instance, if you have an e-stop requirement of SIL 1 from a tolerable risk perspective, you can easily identify some designs that have single points of failure in them and still achieve SIL 1. However, there is almost always a separate requirement in addition to the performance requirement, which says that there can be no single point of failure in our e-stop design. So even though the redundancy is not needed to meet the SIL 1, the redundancy is needed in the e-stop design to meet the no single point of failure prescription requirement in all of these. So again, that is something that we need to keep our wits about us in making sure that we don't ignore a critical set of requirements in all of this. So we've now talked a fair bit around the aspects of layer protection analysis, some of the simplified approaches to that are present in the risk graphs in the standards. And let's look at these and sum things up. So risk graphs, again, very basic, very simple, do not require a lot of data, absolutely sitting in their favor. However, if there's any complexity involved, these risk graphs tend to ignore that complexity and can lead to over-design as a result. Or if we're blindly applying a risk graph that has an embedded risk tolerance already in it that may not be acceptable to us, we may be inadvertently accepting a risk tolerance that is absolutely unacceptable as a result. So again, these things we need to be careful about in applying any risk graph approach. Now, layer of protection analysis also has its advantages and disadvantages. As we've highlighted in today's presentation, it's a very versatile technique. It can be applied to low demand safety function specification. It can be applied to high demand safety function specification. It's a reasonably well understood technique, and it gives us the flexibility to understand the overall accident scenario and how it might develop better to potentially implement more effective protection layers. But on its downside, it's only as good as the data you have to feed into it. It can take a bit of time. And unfortunately, it can be hijacked and reverse engineered to miraculously give you the answer that you wanted all along. And that railroading of the technique is something that you absolutely want to avoid, but that's for another presentation. So in summary, I hope we've presented the LOPA technique as an effective model for risk in both situations where we're considering a high demand and continuous mode safety function, as well as the standard low demand mode safety function that it's most commonly used for from the process industry. And also we've shown how the more generalized LOPA approach can fit on top of the 62061, 13849 simplified risk graph methods of risk analysis. And again, helping us achieve the goal of not only doing the analysis, but understanding the situation and being able to take a set of intelligent actions as a result of that understanding to manage our risk down to a level that we can live with without undue hassle and other problems. All right, now I've got a few other questions that have come up that I haven't taken on quite directly, so let me take some of those at this point. So I've got a series of questions that says, first, when a risk matrix is used for SIL selection, how can we select high demand mode? Well, the risk matrix, if it has the SIL in the boxes, that is inherently a low demand mode technique. If instead a risk matrix is something that you can convert into a set of frequency targets, then that can be a LOPA analysis, and a high demand safety function initiating event can be used to improve the frequency down to a level that is acceptable according to that risk matrix. But yes, some risk matrices will be inherently low demand oriented in their application. Now, hopefully I've addressed that, and we've got another question that is saying that I'm suggesting using a failure rate of the SIF as an initiating event. And yes, the cutoff point. The problem comes when a SIF is actually a not too high demand, for which we might need to consider a PFH to follow the standard, but which we might look at as a functionally independent protection layer. Now, that is an interesting situation, and what tends, and this is where we are doing a vast simplification of the math. And I will admit, almost always that this math is simplified so that even if our safety function is demanded every couple of months, the high demand consideration of that function is going to be a better mathematical model of that situation. And our safety function as initiating event, even with a couple of months of time between the demands, will still be the better math to present that. Now, what you can look at in the extreme, and I'll try and answer this briefly. Let's say you have a high demand safety function which fails once every 22 years. And we consider the difference between a demand every 10 minutes and a demand every 2 months. The actual difference in accident frequency is only going to be once every 22 years and 10 minutes versus once every 22 years and 2 months, which is actually a relatively small overall frequency difference, and therefore fits that modeling of the safety function as an initiating event failure. All right, so next, why is LOPA termed semi-quantitative? Semi stands for partially quantitative when you're using the order of magnitude protection layer simplification. That is, each protection layer gives you a full order of magnitude risk reduction, or you don't take any credit at all. So that very rough quantification is what we use the term semi-quantitative to mean in all of this. Now, there's a separate question about hardware fault tolerance associated with high demand SIFs and low demand SIFs. Yes, there will be some slightly different requirements in the 62061 from the 61508 and the 61511 in all of this, whether you're following route 1H or route 2H in all of this, but that is somewhat outside the scope of today's presentation, and I would direct you toward a SIL verification presentation to clarify that. Now, the next question I've got is let's see here. No, there we are, all right. Should high demand, or excuse me, for semi-quantitative LOPA, what would I consider a basic process control system initiating event frequency? Or no, would I consider a BPCS event frequency of once a year being a high demand on a SIF, assuming that that is the SIF demand rate? Exactly once a year, that's the cutoff. So I do not remember in the standard whether it's a greater than or equal to or a greater than sign, so I don't know which side the exactly once a year demand falls on, but I would check that in the standard. And then I've got one last question, and then we will tie things up. Is there any relation between a LOPA and a bow tie? Yes. A LOPA is a single path through the bow tie. The bow tie is a combination of event escalation sequences that often tie together at a loss of containment point in the middle with various different potential outcomes resulting from that. Now, each one of those lines all the way from the left side of the bow tie to the right side of the bow tie, that can be done as a LOPA. And then when you combine all of those things together, that's what you get with the bow tie. So hopefully that addresses everyone's questions, and actually we're pretty close, right on an hour. So I will simply then direct you to some of the other elements of exida that we would encourage you to take a look at. We have an array of online self-paced training courses that you might find helpful, covering process, machinery, automotive, and cybersecurity. We have an array of upcoming live online course presentations. This is nominally the exida Asia Pacific list that we've got on the screen here. And hopefully some of those may be of interest as well. Okay. I've gotten a couple more questions and I will answer those before signing off. And the first one is, how do we determine tolerable risk in the first place? Does it vary industry to industry? There's not a short answer to this. The goal of tolerable risk is to fit in with society. You look at existing accident rates that society is essentially already tolerating. And then based on what is happening already, whoever owns the risk then has the authority to make a decision as to what level of risk they are willing to accept in that situation. So, revealed risk, Arctic fishing fleets tend to tolerate one fatal accident in 100 years, whereas accountancy firms tend to tolerate one fatal accident every 100,000 years in all of that. So there's a wide range of situations there. And then finally, can we say that a BPCS has a continuous demand for control function, but could have low demand for safety function? Now, this is all down to where in the sequence of escalation the basic process control system falls. Is it in continuous control, and that is the safety action that it needs to carry out, in which case, yes, PFH controls its behavior, or it might be a basic control safety function that is not SIL rated, that could be rarely demanded in the instance of other failures or rare demands on that control function, in which case it's a protection layer and PFD defines its performance. So it's really down to an understanding of the exact situation that you're looking at. All right, so that's all the questions, and hopefully that gives you a reasonable view of layer of protection analysis with high demand and continuous mode applications. So again, thank you very much for your attention, and I hope you found this webinar useful. I'm going to stop the recording and close the webinar now. Thank you again.